I Neha Yadav, Assistant Professor in ABES Engineering College, Ghaziabad. Today I am going to teach the second topic of Unit 4 of Discrete Structure and Theory of Logic. The topic is Semigroup and Monoid. In the previous lecture, I have covered algebraic structure. So here we will take reference with the previous lecture. The definition of semigroup will say an algebraic structure is called a semigroup if the binary operation is associative in G. If binary operation follows the associative property. So, first of all, for semigroup, for checking whether a set is or whether a structure is semigroup, we first of all need to check whether it is a algebraic structure or not. So, what is a algebraic structure? As in previous lecture, I have explained algebraic structure. A algebraic structure is simply a set equipped with a binary operation which follows closure property. And when an algebraic structure follows associative property, then it is a semigroup. What is a associative property? Simply if on changing the association between three operands, we will get same result or we will we will not get any change in the result, then the associative property will be satisfied. So this is the associative property on changing the association between the operands. Here I am applying the operation between AB first and then with C. Here I have applied the operation between BC first and then with A. If we get the same result on changing the association, then we will consider it as associative property will be satisfied. So here the first example of semigroup is set of natural number with addition operation. So for checking whether it is a semigroup or not, first of all we have to check whether it is a algebraic structure or not. As the definition of semigroup says that an algebraic structure which follows associative property is a semigroup. So I have to check first whether it is a algebraic structure or not. And for checking algebraic structure, I have to check the closure property. So what closure property said? Closure property says that if we multiply any two natural number, in this case, if we multiply any, sorry, if we add, here is the addition operation, not the multiplication. So if we add any two natural number, we will get a natural number only. If this is the case, the closure property will be satisfied. So if we consider any two natural number, we will always get a natural number. So these are all natural numbers. So these elements can be anything. If we take any natural number, we will always get a natural number on adding to natural number. So closure property is satisfied. Hence, this is the algebraic structure. Now we will check for associative property. So here we will check for two operands only. So for in case of two operand, the associative property is always satisfied. If we apply addition operation between 1 and 2, and we will go and check for associative property, the associative property is satisfied. So this algebraic structure is following the associative property, or it is following the associativity. So it is a semigroup. The next example is set of natural number with multiplication. Natural numbers are numbers from 1 to, this is a infinite set. So if we multiply any two natural number, for example 300 with 2, we will get 600, which is also a natural number. It will be in this group. So it follows the closure property. Hence it is a algebraic structure. And when we check for, this is the addition and this is a natural number, and we will check for associativity. For example 300 plus, for example 300, here the operation is multiplication. So 300 into 2, we will get 600. So here closure property is satisfied. If we go for the associative property, we will get same result. For two operand, we need not to check. For all the two operands, the associative property will be satisfied. So here also associative property is satisfied. So closure, first one is closure property satisfied. It is a algebraic structure. Second one is associative property satisfied. So it is a semigroup. Now coming to the third example, set of integer with addition. So we will check for algebraic structure. Is closure property satisfying or not? For if we add any two integers, we will always get a integer. So closure property is satisfied. And for any two operands, we will always get 1 plus 2 is always equals to 1 plus 2. We can't change any association here as the operands are 2. So associativity, by default associativity property is satisfied here. So here both closure property and associativity is satisfied. So this is a semigroup. Next topic is monoid. What is a monoid? Monoid is a semigroup if there exists an identity element. There exists an identity element E in G such that E binary operation A is equal to A or A binary operation E is equal to A. For example, this is a algebraic structure which we are considering, or this is any structure which we are considering. For it to be monoid, we first have to prove that this is a algebraic structure, and we know that a algebraic structure should follow the closure property. So we will first check whether this structure is following the closure property or not. If this structure follows the closure property, it will be algebraic structure. Then we will check for semigroup. For semigroup, we need to check associative property. So we will check whether the associative property is satisfied or not. So if associative property will satisfy, this structure will also be a semigroup. Then we will check for monoid. If it is a semigroup, then we will check for monoid. If there is an identity element E in set G, in this set, if identity element exists, then this semigroup will be a monoid. How we will find the identity element? For example, if there are 1, 2, 3 element, okay, with operation is addition. This is the structure, this is the set, and this is the structure. First of all, we will check for algebraic structure. The algebraic structure is, we have to check the closure property. In this case, if we add 3 plus 1, then it will be 4. So here algebraic property is not satisfied. For example, we will consider another example, a set of natural number with addition. If we are considering set of natural number with addition, we will check for closure property. If we apply addition operation between any two natural number, we will get a natural number. So algebraic closure property is satisfied, hence it is a algebraic structure. For this, we will check for associative property. So adding any two natural number, the associative property will be always satisfied, as we cannot change association between two operand, and we are checking just for two natural number. So A plus B will always remain A plus V. So associative property will be satisfied. So this is a semigroup also. Now we will check for the whether it is a monoid or not. So a semigroup is a monoid when there exists an identity element in the set. Here the set we are considering is this. How we will find a identity element? For example, if we consider any element from this, for example, A is a natural number. If we apply this addition operation, or whatever the given operation is, here the addition operation is given. So if we add something to the element natural number, then if we get A, then this value will be your identity element. If we consider simple one natural number and add something to it, so that we can get back the particular element only. If we get this particular value here, and this value is in the given set, for example, natural number, this is in this set, then the identity, we will say identity element will follow. Yeah, identity element exists. For it's a, for in this case, for this case, A plus 0. A plus 0 gives us A. So is 0 a natural number? No, 0 is not a natural number. So this is not a monoid. Clear? This is a algebraic structure. This is a semigroup, but this is not a monoid because 0 is the identity element for this structure and 0 is not in this set. So identity element does not exist. We will take some more examples. This is the another example. Here it is given also. Identity element is 0. Set of integers. Integers are everything like -2, -1, 0, 1, 2, 3 till infinite. It is a infinite set. The operation here is given is plus. So this is the structure we have. So for checking whether it is a monoid or not, here it is given it is a monoid, but we will check how we will find it is a monoid or not. So for checking whether it is a monoid or not, first of all we have to check for closure property. So for any integer with addition operator, does closure property satisfies or not? If we apply addition operation on any two integer, for example 1 or 2, we are applying addition operation on 1 and 2, we will get 3. This is an integer. If we consider any integer, we will get a integer only. So closure property satisfied, hence it is a algebraic structure. So this is a algebraic structure. Now we will check for semigroup. A algebraic structure which follows associative property is a semigroup. So consider any two element. 1 plus 2 is always 1 plus 2. So associativity always satisfied for two operands. Clearly clear? So this is also a semigroup. Now we will check whether it is a monoid or not. What the definition of monoid said? Monoid is semigroup is a monoid when there exists an identity element. So in this case, we will check for identity element. Consider any positive integer or any integer. Here the set is any integer. So we will consider any integer. For example, 2. Operation is addition. So adding 2 to what will give you 2? We know that 0. Is 0 belongs to this set which is given to us? Yes, 0 is present in this set. So here identity element exists. So this is also a monoid. So this structure is all algebraic structure, semigroup as well as monoid. Coming to the next example, if we consider a set of integer with multiplication, we will check for a closure property. If we multiply any two integer, whether 1 or 2, whether 600 or 5, we will always get an integer. So closure property satisfied, hence it is a algebraic structure. Now we will check for semigroup. So 1.2 is always 1.2. Associativity always satisfied for two operands. So it is also a semigroup. Associativity satisfies. Now we will go for checking monoid. A monoid is a semigroup where identity element exists. So here the operation is multiplication and set is integer. Consider any integer. For example, we consider integer as 5. Applying this operation, given operation, multiplication operation with 5, when we will get 5. So this is the way to find the identity element. If when we will get the identity element, then only we can check whether this identity element is in this set or not. So first of all, we have to find the identity element. So take any element from the given set. I am taking here for 5. So applying multiplication operation on 5 with what value we will get 5. So this will obviously be 1. So here for multiplication, identity element is always 1. In last case, we have seen identity element is 0. So for addition, identity element is always 0. For multiplication, identity element is always 1. So here identity element is 1. Now we will check whether 1 belongs to the set of integer or not. Yes, we know 1 is an integer. 1 is in this set. So this is a monoid also. Next, this is an important question. Here we have given the operation is given here. This binary operation is defined by the question itself. So this question says when we apply this operation between any two values, we will get the result as this. Clear? Here we have to check whether this is a monoid or not. The set is set of integers and the operation is this, and the value of operation, the operation is defined by this. This operation is doing this. So we have to check whether it is a monoid or not. So first of all, we have to find whether it is a algebraic structure or not. For algebraic structure, we have to find whether it satisfies closure property or not. So consider any two integer, for example, 1 and 6. It will give, for if we apply this operation, we will apply this operation. It is not 1, just write this. Don't write addition, just write this as the definition of operator is given in the question. If we apply this operation between 1 and 6, we will get the first operand, this first operand plus, sorry, 1 operator. This is 1 plus 6 plus 1. This is the definition. This is x, this is y. Here x, y, and 1. This operation is defined this way. So we will get 7. 7 is also an integer. So 7 belongs to this group. We will check for any other value. 10, 6. 10 plus 6 definition says that 10 plus 6 plus 1. It will be 17. 17 is also integer. So if we check for any two values, we will get a value which will be a integer. So here closure property satisfied. Hence this is a algebraic structure. Now we will check for semigroup. If we consider this example only, if we change the association, it will always, if we add 1 and 6 first and then add 1, we will get same result if we add 6 and 1, this one first and then add this one. So here associativity also holds. We will get 6 plus 1 plus 1, 8, and 6 plus 1 plus 8. So here associativity holds. So this is also a semigroup. Now we will check for monoid, whether a identity element exists or not. So for checking identity element exists or not, we just need to find what the identity element first. So first of all, we will take any one integer value. This value can be 7. Applying this operation, can we get 7? For example, I'm considering the identity element as P. Will I get 7? For what value of P will I get 7? So here I simply write from this I will simply write the definition. This is x, this is y. The definition of this operation saying that x plus y plus 1. So I'm simply writing the definition of x plus y, this operator. And we need to get the value as 7. This is the way to find the identity element. If we apply the operation to any element of the set, then the other operand should be what? We get the first element as the result. So here we will find the value of this P. So the P will be minus 1. This is the identity element here. So minus 1 is the identity element. Is minus 1 belongs to the set. Set is set of positive integer. Yes, minus 1 is a set of, sorry, this is not set of positive integer. This is simply a set of integer. Set of positive integer is z plus. So here minus 1 is a integer. So here identity element is existing in this set. So this is also a monoid. Clear? This is algebraic structure, this is semigroup, and this is a monoid. So briefing this lecture, in this lecture I have taught what is a semigroup and what is a monoid. A semigroup is a algebraic structure which follows associative property. A monoid is a semigroup where identity element exists. So here we have completed three topics of this unit: algebraic structure, semigroup, and monoid. This is the reference book, S. Chand book, a textbook of discrete mathematics. Thank you for patience listening. Thank you so much.